Welcome to our deep dive. Today we're going to be talking about something pretty interesting, multimodal large language models, or MLLMs, as I'm sure you all know them. And they're, well, kind of surprising struggles, actually, with geometry.
Yeah, it is a bit of a paradox when you think about it. We have these models now that can write you a poem or translate languages, even code. And yet, basic visual concepts, they really seem to struggle with them.
That's right. This paper we're looking at, Euclid, supercharging multimodal LLMs with synthetic high-fidelity visual descriptions.
Hmm.
That's really what they're digging into, this what they call the low-level visual perception, or LLVP problem.
Yeah, so in the introduction, section 1, the authors point out that MLLMs, they're great at those high-level tasks, like I mentioned, image captioning, stuff like that. But when it comes to, accurately describing the fundamental geometric components of an image, that's where they fall short. Identifying points on a line or distinguishing between different angles, like that.
And they really emphasize in section 1.1 the importance of low-level visual perception, that this isn't just some, academic thing,
Yeah.
this LLVP.
Yeah.
It's really important for a lot of real-world stuff.
Absolutely. So many applications rely on it. Think about robotics,
Mhm.
self-driving cars, even something like medical imaging analysis. All of those, they need a super precise understanding of shapes and positions and the relationships between objects in a visual scene.
So to really test this LLVP ability in MLLMs, they had to come up with a benchmark data set.
Right, and they called that geoperception. Section 3 is all about how they made it, benchmark creation.
Interesting.
It's derived actually from a high school geometry textbook. So the focus is really on those visual tasks that, we as humans learn early on. But as it turns out, they're surprisingly difficult for MLLMs to grasp.
So in section 3.1 Geoperception Benchmark, they go over the different types of questions, 6 primary types actually, all designed to see how well a model understands different geometric concepts.
So we've got point leads on line, point leads on circle, angle classification, line comparison, perpendicular, parallel, and then there's one called equal.
And that last one, equal. That one's designed to test how well an MLLM understands the annotations in a diagram.
Exactly. It's all laid out in Table 1, Geoperception Task Descriptions. Might seem pretty basic to us, but for MLLMs, it's a real challenge.
Yeah. The results of their tests are in Table 2, performance of various models on the Geoperception benchmark, and honestly, kind of surprising.
Yeah, they looked at a bunch of different MLLMs, both open source and the big commercial ones, but none of them did all that great on geoperception.
And they show that pretty clearly in figures 1 and 2, performance comparison across models and accuracy of different models on tasks, even the big names, like Gemini, really struggle. So this LOVP issue, it's pretty widespread.
Yeah. Take the point leads on line task, for example. Not a single MLLM got even 30% accuracy. Pretty big difference from how a human would do.
Makes you wonder, right?
Yeah.
Like, these models are so good at other things, but what is it about those basic visual relationships that trips them up?
Well, so the researchers, they kind of took a pretty interesting approach to tackle this. They created a synthetic geometry image generation engine. That's how they created their training data. That's all in section 4, Euclid. Synthetic data for low-level visual perception.
That is interesting, that synthetic data approach. Why not just use, real images?
So they explain that in section 4.1, motivation for synthetic data. The thing is, real-world image data sets, they usually don't have those precise geometric annotations that you really need to train an MLLM for these LLVP tasks. Like you might have a photo of, say, a bridge, but will it have all the lines and angles perfectly labeled? Probably not.
Ah, I see. With synthetic data, though, they can control everything, right?
Yeah.
Generate all sorts of geometric shapes and label them perfectly.
That's it. It's like a visual textbook for the models. They describe the engine in detail in section 4.2, Synthetic Geometry Image Generation Engine. All kinds of shapes and complexities, just like you'd find in a textbook.
So it's not just spitting out random shapes. This engine, it also generates text, right? Describing the shapes. That's in section 4.3, text generation for synthetic data.
Yeah, so for each image, you have a description of all the geometric properties laid out just like you'd see in a textbook problem. It's like they built a system that can come up with an endless supply of geometry problems, diagrams, word problems, the whole works. And it's all perfectly designed to teach these MLLMs.
So they've bypassed that whole problem of real-world data sets not being detailed enough. They've created this perfectly controlled training environment.
You got it. And with all that data, they were able to develop a series of models, which they call collectively Euclid.
Euclid, clever name, given that, Euclid is considered the father of geometry. So how did they actually go about training Euclid with this synthetic data?
Well, that's in Section 5, Training Euclid. Lots of steps involved, but the first thing was figuring out the right MLLM architecture. Basically, which type of neural network is best at pulling out that geometric information from the images.
What did they end up going with?
In Section 5.1, Model Architecture Exploration, they talk about how they found that convolutional neural networks, CNNs, did better than the vision transformers, or VITs. Kind of a back-to-basics thing.
Interesting. Why do you think CNNs were a better fit for this kind of task?
Well, the researchers think it might be because CNNs are better at processing those local features in an image. The edges, corners, that kind of thing, and those features. They're super important for understanding geometric relationships.
Right. Okay. So we've got the data, the architecture.
Yeah.
What else was important for making sure Euclid learned effectively?
They talk about a couple of things in Section 5.2, training strategies. One big one was fine-tuning the visual encoder during training. That's like adjusting the part of the model that actually processes the images. Made a big difference.
And then there's the thing I was most interested in, curriculum learning. They go over that in section 5.2.1.
Yeah, curriculum learning is pretty cool. Instead of throwing every shape and problem at the model right away, they structure the training data in stages. So it starts with really simple shapes, then the complexity gradually increases.
Kind of like mimicking how humans learn geometry, right? Start with the basics, points, lines, angles, and then build up to the harder stuff.
They're definitely taking inspiration from Euclid himself.
And in section 5.2.2, data smoothing, they talk about, well, data smoothing.
Ah, right. They use that to make sure Euclid didn't forget the earlier stuff as it went through the curriculum. Kind of like making sure it doesn't forget the basics as it learns more advanced concepts.
So curriculum learning, was it effective?
It really was. This whole staged training approach, it worked way better than just giving the model everything at once. They saw that it really helped Euclid learn better and be able to generalize its knowledge to new situations.
Okay, so now we have Euclid trained up on this carefully designed synthetic data. So how did it stack up against those other MLLMs that struggled so much with geoperception? Did they manage to make some progress with this LLVP problem?
Yeah, the results were pretty impressive. Even though it was only trained on that synthetic data, Euclid was able to generalize really well to the real-world geometry problems in geoperception. It's all in Section 6, Evaluation and Results.
Okay, so how did it compare, like head-to-head, with the other models?
It consistently beat them. Like on that point lease online task, the one that really tripped up the other models, Euclid got over 80% accuracy.
Wow.
Yeah, it's a huge jump from, less than 30% that the best commercial models were getting. You can see that in Figure 3, performance comparison on point lease online task.
So using that synthetic data and the curriculum learning, it really seems like that paid off. Did they give any specific examples of how Euclid actually tackles these tasks?
They did, yeah. In Appendix C, geometry shapes used in Euclid's training, they give a really detailed breakdown of all the shapes they used. They even include the code for generating them and some diagrams to illustrate.
That's good. It's always good to see that kind of transparency. What kind of insights did they get from those examples?
So for that point lace online task, they started Euclid off with super simple shapes in that first stage of training, like triangles. The text descriptions would be, very straightforward, like stating which points were on which lines. Figure 9a shows that visualizations of different tasks, and the text with it says points B and C lie on line AC.
So starting with the very basics, just like you would with, a human student,
Yeah.
then how did they ramp up the difficulty as the training went on?
In stage 2, they brought in circles and that idea of midpoints. You can see that in Figure 9b. And for that one, the text says point B is the midpoint of line AC.
Okay, so building it up step by step. What about the final stage?
That's where things get really complex. More intricate shapes, like the ones in Figure 9c. Now the model has to deal with lines that intersect different shapes, understand more complicated relationships between all those geometric elements.
It makes sense that gradual increase in complexity would be so important for Euclid to, really learn effectively. But even so, no model's perfect, right? Did the researchers find any areas where Euclid still struggled?
Yeah, and they're really open about that in Section 7, Limitations and Future Work. One thing they noticed was that when diagrams had a lot of annotations, Euclid could get a bit confused, just like other MLLMs.
So it's not just about understanding the shapes themselves, it's about how those annotations give extra information about the relationships, right?
Yeah, sometimes all that extra visual information can be a bit overwhelming for the models. In Figure 8, they show an example where the model gets it wrong. identifies a point on the wrong line, probably because it's getting distracted by the other annotations in the diagram.
So even Euclid, impressive as it is, there's still work to be done. What are some of the things they suggest for future research to, address these limitations?
They think that one way to improve LLVP would be to include a lot more variety in the annotation styles in the training data. That would help the models get a better understanding of all the different ways we can use annotations to represent these geometric concepts.
Give them more experience with, the different visual languages we use for geometry.
Exactly. And they don't want to stop at 2D geometry either. They even talk about expanding the data to include other visual domains, like moving beyond simple shapes and into, more complex real-world objects.
That's a cool idea. Imagine models that can really understand the geometry of the world around us, not just in diagrams, but in, all the complexity of everyday scenes.
That's the goal. And they think that what they learn from Euclid, especially that synthetic data and curriculum learning, that those ideas can be applied to these other broader areas as well.
That's promising. It seems like this research, even though it's focusing on something as, seemingly basic as geometry, it's really opened up a new path for improving how MLLMs understand visual information.
For sure. By really getting down to these fundamental LLVP problems, they've laid the groundwork for models that can, really see the world with much more detail and accuracy.
And it's really great that they've shared all the specifics of their work. The code for their data engine, the training stuff, even the evaluation prompts they used, that's all in Appendix B, evaluation prompts.
Yeah, it's nice to see that kind of open approach. It means that others can build on what they've done and, push these ideas even further.
Well, this has been a really interesting deep dive into a surprisingly complex topic. It seems like even something like geometry can teach us so much about what these MLMs can do and where they still need to improve.
Yeah, it really shows that, even though these models can do some pretty amazing things, they're still kind of in their infancy when it comes to this visual understanding stuff.
And research like this is really important, right, to figure out where those gaps are and how to close them. Did the researchers talk about specifically what this could mean for other areas where visual understanding is key, like robotics?
They did a little bit in section 7.1, future research directions.
Yeah.
They suggest that, what they learned with Euclid, especially the synthetic data and the curriculum learning, that could be really useful for training robots to, perceive and manipulate objects better.
So instead of just using real-world data, you could create these simulated environments
Yeah.
with everything perfectly labeled, and then the robots could learn way faster and, it'd be safer too, more controlled.
That's the idea. And they even talk about like medical image analysis using MLLMs to spot those tiny visual patterns that maybe a human doctor wouldn't catch.
That's pretty exciting to think about. Imagine, models that could help doctors make more accurate diagnoses because they can analyze images with so much detail.
It's definitely an area with a lot of potential. And it all comes back to, tackling this basic LLVP problem, which, like this research shows, it's not as straightforward as you might think.
Well, this has been a really fascinating look at geometry and MLLMs. What do you think is the biggest takeaway from this research?
I think it's that, we can make real progress on this LLVP stuff, but we have to really focus on the fundamentals. Creating good synthetic data, designing the training process carefully, using techniques like curriculum learning, that's what can really boost these models' ability to actually perceive and make sense of visual information.
And it's not just about those abstract geometric shapes either. The researchers think these principles, they can be applied to much more complex, real-world stuff. Maybe even revolutionize fields like, robotics or medicine.
It's a good reminder that as impressive as these MLMs are, there's still so much more they can do. Research like this, it pushes the limits and opens up all these new possibilities.
Well, this deep dive has definitely given me a better understanding of how complex these MLLMs are and all the potential they have. Clearly, they're not just, good with language. They can be powerful visual learners, too. Thanks for taking us through all of this.
Happy to do it. It's always fun to dig into this kind of cutting edge stuff and see where it all might lead.